So now we're going to go through and we're going to utilize our knowledge about polynomials to talk about rational functions. So a rational function is just a function in a specific form. You think of rational numbers, that's an integer over an integer. A rational function is one in the form where you have p of x divided by q of x, where both of these are polynomial functions. The one thing you want to make sure is that the denominator does not equal 0. So this is our rational function. The denominator is going to be the set of real numbers so that you're not dividing by 0. So we've already dealt with finding domains of rational functions. Well, let's just look at a nice example. We've got f of x is x minus 5 over 3 plus x. We want to find the domain of this and we want to state it in interval notation. So we need that denominator to not equal 0. So we want x to not equal 3. So what that means is we want that denominator to not equal 0, so x can't equal negative 3. So every other value is perfectly fine except this. So in interval notation, that's from negative infinity to negative 3, or from negative 3 to infinity. In the case you try to plug in x equals 5, that's perfectly fine. So a lot of times a confusion will happen in that you think 5 is problematic because it makes the numerator equal 0. But that's no issue. When you plug in 5, you get an output of 0 because the bottom is just going to be 8. 0 over 8, still 0. These actually give you what those x-intercepts of this rational function will be. So just be careful. Remember, you can't divide by 0, but you absolutely can have 0 in the numerator of a rational function. Okay? So now we're going to discuss 3 types of asymptotes that can possibly happen when we deal with these rational functions. So something we're going to use pretty frequently is this arrow. So it means approaches. So if we think of the statement f of x with the arrow to infinity as x right arrow 0, and then we've got this little notation of a plus 2. This means f of x approaches infinity as x approaches 0, and this plus means to the right. So the idea is, if you look at this function, this would satisfy exactly what the statement says. As you're approaching 0 from the right-hand side, so I'm coming in on the right, the y values are blowing up to infinity. So the function is approaching infinity. If I think of a different statement that's slightly similar, f of x approaches negative infinity as x approaches 0, and this means to the left. Okay? So the positive means right because you think of it as the positive side of 0. The negative means from the left. So in this case, if we want a graph that satisfies this, as you come in from the left-hand side of 0, the y values are going down and approaching negative infinity. Okay? So in each case, x equals 0 is going to be a vertical asymptote. So pretty much your function has to grow unbounded in the y values. These asymptotes mean that your function's getting really, really close to this line. And we have 3 types of lines: vertical lines, horizontal lines, and then you have a line that has a slope to it. Those are the 3 types of asymptotes we're going to occur. Now, to actually find the vertical asymptotes, you basically want to end up dividing by 0. Because if you're dividing by a very small number, it's going to get bigger and bigger. 1 divided by 1, not so big. 1 divided by 0.01, a lot bigger. 1 divided by 0.000000001, even smaller. You know you can't take, or even bigger. You know you can't take 1 and divide it by 0, but that's kind of the idea you want to keep in your head. If you divide by 0, it's potentially going to cause your function to blow up. Not always, though, so don't get confused. So the way we actually want to locate it is you have to reduce the function to lowest terms. So basically cancel out as much as you possibly can. Then you're going to go ahead and set the denominator equal to 0. then those will be where our vertical asymptotes will occur. Now the thing is, an asymptote is an equation of a line. So you've got to express the vertical asymptotes as the equation x equals some number. Now, if it does happen that when you go to cancel out factors, the problematic point in the bottom completely disappears, that's fine. You still can't equal that number because it caused you issues at some point, but it's not going to correspond to a vertical asymptote. Instead, it's going to be a hole in the graph at that specific point. So we'll see an example of that. Let's go ahead and find the vertical asymptotes of a few functions. So I'm going to start with this function 2 minus x over x cubed plus 2x squared plus x. I've got to reduce this, so that means I've got to factor it. And really, you want to factor anyway because that's going to help you figure out where the asymptotes occur at. Can't do anything in the numerator, but in the denominator, I could take out an x, and then the bottom factors nicely into x plus 1 squared times x. Now, I can't cancel anything out. Neither of these look alike, so that is going to be in our lowest terms. So I'm going to have two vertical asymptotes. The first one occurs when x equals 0. Second one occurs when x plus 1 equals 0. So your first vertical asymptote is the line x equals 0, and the second one is x equals negative 1. So those are our two vertical asymptotes. Now if we look at this next example, it's already factored for us, which is nice, and we do have some factors we can reduce. So I've got 2 up top, 1 in the bottom. The 2 is going to cancel, and this one will disappear. So we get x plus 4 over x minus 2. Now, we still can't have x equals negative 4. That would cause us problems in the domain. Okay, and I dropped a minus sign. It should be x plus 2. So let's take a look at this next one. It's already in factored form for us, which is great. And if you notice, I do have some repeat factors in the numerator and denominator. I've got more in the numerator, so 1 is going to cancel, and I'm going to be left with 1 up top. Now, I still can't have x equals negative 4 because it did cause us problems, and same thing with 2. These are excluded from the domain, but x equals negative 4 is not going to cause any issues because in this resulting expression, I have no issues with negative 4. So what this means is our vertical asymptote is at x equals 2, but we're just going to have a hole at x equals negative 4 instead. Okay. If we look at one more example, same type of thing. Now I've got more factors in the bottom. So one of the x minus 3 cancels in the bottom, and the one from the numerator is completely gone. So we get 1 over x minus 7 squared times x minus 3. So in this case, I've got two problematic points, 7 and 3. So x equals 7 and x equals 3 will be our vertical asymptotes. Okay. So always make sure you reduce it first before you go about finding the vertical asymptotes. Your domain, though, you should always do with the given function. So look at the values you have to exclude right away. Now, a horizontal asymptote gives us the long-term behavior as x approaches positive or negative infinity. So vertical means the y values are growing unbounded. Horizontal means the x values are growing unbounded. So it's giving us really the long-term behavior of the function. So I've got this horizontal line, y equals b, and if I draw a function, it's going to hug this asymptote. It can cross it no problem, but it's going to hug it at that end behavior. A vertical asymptote I'm not going to be able to cross because that would cause us to divide by 0, but you can absolutely cross a horizontal asymptote. To find it, we're really just going to look at the degree of the numerator and denominator. So we've got 3 scenarios that will tell us exactly what the horizontal asymptote is, or if there even is one. So first, if the degree of the numerator is smaller than the degree of the denominator, then y equals 0 is your horizontal asymptote. If the degrees are exactly the same, then you're going to look at the leading coefficients. Their ratio is the horizontal asymptote. If the degree of the numerator is bigger than the degree of the denominator, you won't have a horizontal asymptote. So let's go ahead and look at 3 examples so we can see each of these instances. First, we want to look at those highest powers. So be careful if they're not in order, you want to go ahead and make sure. So let's go ahead and look at 3 different examples. So you want to be careful if your polynomial is not in order, you want to make sure you rearrange it. So in this case, the highest power in the numerator is 7th. In the bottom, it's 4th. So the degree of the numerator is bigger than the degree of the denominator, so there's no horizontal asymptote. If we look at this next one, we've got the 9th power, we've got the 9th power. So the degree of the numerator is exactly the same. So in that case, I'm going to look at the coefficients attached to them. We've got 5 and 12. So the horizontal asymptote is the line y equals 5 over 12. So you just take the coefficient that's attached to it. And then finally, in this last case, we've got x squared up top, x to the 4th in the bottom. So the numerator is smaller than that of the denominator. So y equals 0 is your horizontal asymptote. Okay. So all you really need to do is kind of quick glance look at these. In this last case, or in that first case, when you don't have a horizontal asymptote, it's possible you have this third type that's going to be our slant, or sometimes you might hear it referred to as an oblique asymptote. So in the case that the degree of the numerator is exactly 1 more than the degree of the denominator, there's going to be a slant asymptote. To find that, you're going to actually do long division or synthetic division if that applies. So you're going to take the numerator, divide it by the denominator. Whatever you get as your quotient is going to be your slant asymptote. So you don't care about the remainder, you don't care about the divisor at that point, you just care about the quotient. So let's look at an example. Let's find a slant asymptote for this specific function. So we have a 1st degree polynomial in the bottom, 2nd degree up top. So the degree of the numerator is exactly 1 more. So what we can do in this case, because it's x plus 5 in the bottom, we can go ahead and use synthetic division. So we want to go ahead and divide the numerator by x plus 5. So we get a negative 5 out here. We put all our coefficients, 2, 7, negative 10. Bring the 2 down, multiply by negative 5, add together. Multiply by negative 5, add together. This remainder, don't care about one bit. All I really care about are these 2 coefficients here. So remember, this dealt with x squared terms, x to the 1st, x to the 0. This now becomes x to the 1st and x to the 0. So the equation of our slant asymptote is 2x minus 3, and that's y equals. So it's got to be the equation of a line. Okay? So we can utilize this to help us graph now and get really accurate pictures, or at least as accurate as we possibly can by hand. So we want to graph the function by finding all the asymptotes, any intercepts, and doing any additional plotting as needed. So you're not going to be able to get super precise by hand, but we're going to go ahead and we're going to try our best. So let's start with the vertical asymptotes. We've got the bottom being x plus 1. I can't simplify this at all. So x equals -1 is our vertical asymptote. We've got a second degree up top, first degree in the bottom. So when we go to find the horizontal asymptote, there's none because the numerator is a higher degree than the denominator. We can actually find a slant asymptote because the degree of the numerator is 1 more than the degree of the denominator. So we're going to go ahead and use synthetic division. We got a -1 because we're dividing by x plus 1, 1x squared, no x's, and 5's. Bring the 1 down, multiply, add, multiply, add. Don't care about that 6. I only care about these two pieces here. So y equals x minus 1 is our slant asymptote. So now let's just find a few more points. Let's find the x-intercept. That's going to be when our function equals 0. Well, we can go ahead and cross multiply because it's an equation, it's not an inequality. Subtract 5 to try to solve for x, but you're going to get imaginary numbers. So there are actually no x-intercepts. For the y-intercept, you go ahead and just evaluate at 0, so you get 5. Our y-intercept is 0, 5. Now for some more points, if you go ahead and just pick a couple of values that we haven't used. So we use 0, so that's not going to be in between here. Same thing with -1, can't equal that. That's our vertical asymptote. So this just gives us a good idea of different points on our graph. So what I'm going to do is I'm going to apply all this information to get as accurate as I possibly can. First, I'm going to go ahead and I'm going to plot those asymptotes. So x equals -1 is our vertical asymptote. So we'll go ahead and sketch that in. Then we've got the line x minus 1 as our slant. So that would go through -1 and it has a slope of +1. So this is our slant asymptote. Y equals x minus 1. Now we plot our points. When x equals 0, our output is 5, which is up here. When x equals 1, the output is 3. X equals 2, we get 3 again. And then if you plug in -1 or -2, the output is -9, which is down here. -3 gives you -7. -4 gives you -7 as well. So we're going to hug those asymptotes. And we get our graph of f of x. Okay? So always go through, find all the different asymptotes, plot those, find some extra points just to help guide you. Do as best as you can to be accurate, but again, when you're drawing by hand, it's going to be a little bit difficult. So let's give one more try. Same directions. We're going to plot it. We're going to find all of the important pieces of information. So first and foremost, I want to factor this thing as much as I can because maybe some stuff will cancel. So if I look at the numerator, all of them have a 3, so we can go ahead and take that out. The bottom also factors very nicely as x plus 4 squared. Then our top factors even more. So nothing cancels, so that's good. We're fine. Now we'll utilize this factored form to find all of the important information. Problem in the denominator is when x equals -4. So x equals -4 is our vertical asymptote. If we want to go ahead and we want to figure out if there's a horizontal asymptote, it's the same degree. So I'm going to look at those coefficients. So really you get y equals 3 over 1, or really just y equals 3 is your horizontal asymptote. Because you had a horizontal, there's going to be no slant, but again, follow those directions of one more in the top than the bottom. Now let's find our x-intercept. So we want to set this equal to 0. Really, that's just where the numerator equals 0. So we get two values, 2 and -1. So one x-intercept is at 2, 0. The other is at -1, 0. For the y-intercept, plug in 0, and you're going to get a small decimal. So we're not going to be able to graph it super precisely, but at least it gives us an idea. And then if you pick some more points, here's some other ones that would fall in the graph. So now let's utilize this to get as accurate of a picture as I possibly can. Our horizontal asymptote was at y = 3. So we'll sketch that in. Our vertical asymptote is at y = -4, or x = -4. You absolutely can cross this horizontal asymptote, and if you notice, we actually do right here. When you plug in -2, your output is going to be 3. We know -1 is a 0, 2 is a 0. Our y-intercept is -3.75, which is roughly around here. When you plug in 1, it's like -0.4. So you've got to hug that vertical asymptote, go through all these points, and then you're going to have to come back and hug the horizontal. And then I didn't show it picking any points from the left, but if you pick like -5, -6, you're going to see that you're going to have some positive values. So your graph will be up in this piece here. So just do your best to graph these. Again, you're not going to be able to do it precisely. Most of your homework, though, you're going to be just picking from the graph, or you'll have to plot points, connect the dots.